Relativity of colocality is a ghost of quantum non-locality. The topic of this talk involves things like quantum space-time, interpretation of quantum mechanics, quantum foundations, that type of area. So it's in three main parts. The first part is quantum non-locality, which is also known as Bell non-locality, and Einstein's spooky action at a distance. So Einstein's spooky action at a distance, it was referred to this quantum non-locality. I'll then talk about a special relativity topic, the relativity of colocality, and then I will talk about the parallels between these two phenomena, which are apparently quite different. So quantum non-locality, in brief, this is quantum non-locality is a correlation between entangled particles which defies any classical explanation but does not violate causality. So it originated in, most famously in 1935, where Einstein talked about spooky action at a distance. So what happens in a typical experiment, two entangled particles become separated and then are measured by two observers, which are traditionally called Alice and Bob. So these two observers make measurement choices X and Y and measure outcomes A and B. And there may be some past factors, lambda, which past causal factors. Okay, so what you would expect is that the probability that Alice sees for measuring her outcome A depends on what she did, her preparation, and of these past causal factors. Same deal for Bob. So you would expect overall probability just to be the product of these two. But that's not what happens in quantum mechanics. There's more correlation than this. And so which is mysterious, how that can happen. So in this long review paper, the author, he makes a short comment that locality is the crucial assumption behind this equation here, or in more detail, this one. And in relativistic terms, it's the requirement that events in one region of space-time should not influence events in a space-like separated regions. The problem with this is there are two types of distance, coordinate distance and invariant space-time intervals, which is these are quite different, and these are being mixed up here. So the properties of these two are being conflated, and this, in my view, is a major problem. So here are some of the features of non-locality. I'll come back to more of them later. I'll just mention a couple. Correlation without causal influence, an indeterminacy of spatial location, which is what non-locality means really, a single inseparable non-local event. So there's actually no problem with any of these. Perhaps things are just weird in quantum mechanics, and that's the way it is. We can't really object to that. But the problem is all these things conflict with accepted notions of space-time. So there's no problem with quantum mechanics per se. The problem is it doesn't make any sense in terms of our understanding of space-time. And so again, the problem is it's not a quantum problem, it's a space-time problem. So let's look at space-time. Okay, so special relativity. The Lorentz boost is the velocity transformation in special relativity, and this matrix is symmetrical. This means the Lorentz boost is symmetrical in x and ct, so for all phenomena related to the x boost there's a space-time symmetry. So for the relativity of simultaneity we have the companion phenomenon, the relativity of colocality, and I write about that here in this paper. All this means is inertial observers disagree on which events occur at the same spatial location. Essentially equivalent to there's no absolute state of rest. This is very familiar, but it's underappreciated, the consequences of this. But this is very solid because it's based on this symmetry. The rest principle, which is what I call the rest principle, each inertial observer is physically at rest. And you could argue with this one, definitely. But this is something what I'm saying here is that it's not a question that each observer is of an unknown velocity or it's conventional or arbitrary or something. I'm saying each observer actually is at rest, really is at rest. So here's an example based on that idea. This moose is standing in the middle of a straight highway. Two pickup trucks are travelling in opposite directions as they approach. There's a three-way glancing collision between all three of them. The vehicles carry on in their original heading, but the moose is fatally injured. So the two drivers watch the animal falter in their rear view mirrors. So based on the rest principle, each of these three believes itself to be motionless. So A observes the moose move eastward from the collision site while it's dying, and whereas B sees it moving westward. The moose disagrees with both and finds itself dying motionless on the spot where it was struck. So we have three different stories. So let's consider everyone together, the ensemble of all observers, A, B and M. First of all, the observer M, the moose. This is the collision. This is a space-time diagram. So everyone is simultaneously co-located at C. This is the best we can possibly do and get everybody coordinated. If they can't agree after this, they'll never agree. Okay, so the moose thinks it remains co-local at the same location as C for the rest of its life until it dies at D, with A and B off at either side. Fair enough. This is the same diagram for the moose. Observer B thinks he is co-local with the collision, and with other two off to one side. Same deal for observer A, who thinks he remains co-local with event C. So three different stories. So they disagree where the moose. There's three different opinions on where the moose was when it died relative to event C. Okay. Now, for the ensemble of all observers, so we consider everyone together, we get this diagram. This is simply this diagram, all these three on top of each other, so this event C is drawn at the same place, and you get this. So, again, excuse me, everyone is simultaneously co-local, it's the best we can possibly do, and they all agree. Best we can do, and they agree. But all observers both are and are not co-local with C. There's always somebody who thinks they're co-local, but also other opinions they're not co-local. So for the ensemble, for everyone together, the location of event D is indeterminate relative to event C. If you were to ask everyone together, where was D relative to C, you would hear three different answers. It's not determinate. There's no determinate. That's what this says. And also, we have spatial correlation. So not only indeterminism, but also spatial correlation, because these three spatial locations are correlated, because the moose died at all three. Same event happened at three locations. I'll be saying this a lot. For the ensemble relative to C. This is what this is all based on. So for the ensemble relative to C, the location of the moose's death is indeterminate. So you might object, okay, you say that I've improperly conflated reference frames. I should just look at one at a time. But I would say the physical system consists of all these observers. They all coexist. Therefore, we should be able to describe the system all at once. We shouldn't be prohibited from talking about the whole physical system. That's sort of weird. I mean, that's sort of wrong. And also, because I'm treating everyone the same and talking about everybody in the same breath, I'm following the principle of relativity. Alternative objection you might say, well, we should just ignore the observers completely because they disagree. Forget about the observers and just think about invariance like the space-time interval. This is a very common view, but ignoring observation is in direct conflict with quantum theory, because quantum theory is based on observables. We need compatible philosophies. What this is actually showing is that the normal philosophy of relativity and quantum mechanics are quite different, because this is the normal approach, talk about the invariance and ignore the observer. Okay, and the third thing I should mention is, if this seems sort of weird, well, good. We're trying to get something which is similar to quantum non-locality, which is weird, and this is weird. So that's an advantage of this approach. Okay, so I found the spatial correlation. I'm claiming it feels like quantum non-locality. Let's just compare side by side these two phenomena. So this column, an entangled quantum system, so two particles, say two photons. This side, the moose and the trucks, which is an ensemble of classical inertial observers. Okay. So correlation without causal influence. Well, we have that in the quantum case, and we have it in this case because measurement outcomes at the event D are correlated. The moose always dies, but no event is the cause of any other. So it makes no sense to say this death caused this death. It makes no sense. Exactly the same way in the quantum non-locality, the EPR experiment, it makes no sense to say one event is the cause of the other, but they are correlated, and these are of course correlated. So it's the same thing, very close to the same thing. Indeterminacy of spatial location, we definitely have that in the quantum system, and we have that here. This for the ensemble relativity event C, the location of D is indeterminate. Yes. Correlation is immune to distance. Yes, this quantum experiment has been done many kilometers, and this could be many kilometers as well, because this separation between here and here could be kilometers. Same. A couple more. Single inseparable non-local event. This phrase was brought up by Shimony to express how weird this quantum non-locality is. And yet we have that here. The death of the moose is a single inseparable event, and yet the observers report different locations relative to event C. So we have a single event which is not localized. It's in a slightly different sense from the quantum one. It's not the same, but the analogy is clear. Another one, random element in measurement process. Yes, of course, quantum mechanics, we have that all the time. And we have that here. If you're going to ask the ensemble, who actually is really collocated with C at the time of the death, and you could not get a deterministic answer. The only way you could get an answer at all would be from a coin toss, or you could ask, where did the moose die relative to event C? You cannot get a deterministic answer. The only way you could get a answer, a specific answer, would be at random, same as in quantum mechanics. These are very strong parallels. If you look at the literature of quantum non-locality, you don't find anything like this, at this level of correspondence. So, in conclusion, the starting point is the symmetry of the Lorentz boost. And we found that an ensemble of inertial observers is the classical limit of an entangled quantum system. This is a very strong indication that quantum non-locality is fully compatible with special relativity. I haven't shown that yet, but it's tremendously strong clues that must be the case. And this leads to a new theory of quantum space-time, which there's some information about that here. and that involves relating this ensemble of inertial observers, the moose and the two trucks, relating that to a momentum superposition. Thank you.